thank you, in a sense, for inviting me to give these lectures. I'm eager to give them, and this is when I chose to give them, even though this is a very busy time of the year, and I hope this will not impact the clarity of the lectures. I should say that the lectures are going to be partly delivered via slides, via Keynote. I'm using some presentation I prepared less than a year ago, and I will complement it with here and there, perhaps more in the second part, with handwritten parts. My writing is not good. I cannot organize myself on the page. It's always a mess when I do that. I hope to deliver properly on this part, but I think it's important to have a part that is done like vivo, like it, as if it was a blackboard. So on the subject, let me share the screen, and okay, so it's visible, right?
Yes.
Riccardo, okay. So beyond the standard model, okay. So normally lectures or seminars, lectures on beyond the standard model are organized in the following way. There is a quick analysis or reference to the successes and non-successes of the standard model, an emphasis on the problems, which we know what they are: dark matter, baryogenesis, strong CP, hierarchy problem, cosmological constant problem. And then beyond that, there is normally one focuses on one or more problems and identifies classes of solutions and discusses them, and elucidating their phenomenological implications. Okay, so it's normally organized that way. Now, these lectures are gonna to be a bit different than that. Okay, more than a set of models with their implications. The main goal here is that I want to give you, I'm trying to give you a perspective, okay? A perspective on the formulation and on how to formulate and appreciate some of these problems. In particular, I will focus on the so-called hierarchy, electroweak hierarchy problem, okay? So I know that in this way, things are harder. The risk on stepping on more vague aspects is there, and but I think it's very important to give this perspective, especially in these years, okay, where I have the impression that is going to that is being it's missing, okay? It's often being forgotten or just dismissed, and and especially the case after so there is the impression that things have changed in a significant and dramatic way after the LHC. In fact, the perspective I'm giving you, I mean, in my perspective, so the perspective I'm going to present, while it's influenced in the tone and the emphasis of what happened in the last 10 years, basically could have been presented this way 20 years ago. And in fact, unfortunately, this is the structure of the BSM lectures I've been giving since the first time I gave them, okay? So in order to give this perspective, the only way to start is to emphasize what we know, okay? And what we know is the standard model, and analyze it in a critical way. So in a sense, more than beyond the standard model, actually a number that I really don't like very much, because it gives this idea that something should happen, some sort of eschatological liberation or revolution. So more than beyond the standard model, this course, for a good part, could be called behind the standard model. Okay, so if you want, it's a critical and structural appraisal of the standard model and of the ideas that try to address its shortcomings. As you will see, there is no free lunch in either one way or the other. And that's precisely the centerpiece of these lectures. Okay, so so this is roughly the subjects I will cover. This is a bit the structure of these lectures. So the first lecture may be part of the second, depends. It's not clear to me how much time it will take with the part where I'm handwriting. So the first part is going to be concerning the effective field theory ideology. You've had a series of lectures by Roberto Contino on effective field theory, which are mostly on the technological side, okay? And now ideological doesn't mean that I'm just picking words and nothing else. Of course, by ideology here, I'm trying to draw the general conceptual and structural lessons from effective field theory, okay? And effective field theory, in terms, I say ideology because the effective field theory construction will give us a perspective on how to pose and ask the questions, okay? So in that sense, it's an ideology. And after I've introduced the basic idea behind this, and this will be done today, we will apply this ideology, this ideological perspective to the standard model, okay? And evaluate its pluses and its minuses in the light of this perspective. And this, starting from as a consequence, if you want, or motivated by the minuses, we will introduce BSM scenarios, for instance, supersymmetry and composite Higgs, and in the same way, analyze their shortcomings, okay, the pluses and their minuses. And the essence of this comparison with the standard model and its extensions will essentially end up in a formulation of what we call the hierarchy paradox. So the hierarchy paradox, the way I will present it, is not really called the hierarchy problem. It's a paradox. It's introduced, if you want, at the end, after having seen both the standard model and the BSM models. Okay, this to me is I believe is the modern way to present it. If time permits, I will also spend time try to discuss a few more ideas. I don't know, like larger dimensions, or perhaps like unnaturalness, or maybe the relaxation mechanism, relaxant. I'm not sure I will have the time to do that, but let's see. Okay, so let's start with effective field theory. Okay, so so there are two basic notions associated that stem from that are associated with the modern effective field theory perspective on particle physics and quantum field theory in general. And these two notions, universality and reductionism, are actually of broader validity than just they're broadly more relevant than just the domain. They're not just limited to the domain of particle physics. They are essential to our way of doing, and even to the why we can do physics. Okay, and so I want to spend the first few transparencies illustrating these two notions. Okay, and before starting the illustration with examples, let me at least set the stage for what we are doing. Okay, so as you see, reductionism has to do with probing distances, okay, looking inside. So let's remind ourselves what we are doing when we do particle physics. Okay, so we are doing we're putting together quantum mechanics and relativity. Okay, and so quantum mechanics relates length scales to momentum scales. Okay, probability waves. Okay, so you can associate the momentum to the wavelength of the wave function. So there is a, speaking about length, going to short distances, if you want, is like going to high momentum. And relativity is equating momentum, energy, and mass. So going to large momentum is equivalent, is the same as going to large energy. So going to large energy is going to short distances, and therefore going inside, okay, looking better and better and better. That's the essence of high energy physics. It's not that we want to have higher energies, we want to have shorter distances. And that's the essence of the game. Physics has been since long, physics, but all of science, even biology, a motion towards, I mean, a good part of physics. Of course, there's also astrophysics going far away, but a good part, half of physics has been going to shorter and shorter distances. And it is in this context that the notions of reductionism and universality arise. And let me just illustrate them with a very simple example, the electrostatic potential, okay? So consider a very basic physical situation, one in which you have a distribution of electric charge localized in a finite region of space of dimension A, size A, and you're looking at the field at a distance r that is much, much bigger than the size of the object. Okay? As you're familiar from electrostatics, in this situation, it makes sense, it is possible to write the electrostatic potential in terms of a multiple expansion, okay, where you have contribute, and this multiple expansion is made of terms that decay with bigger and bigger powers with r, okay? So it's a series in inverse powers of the distance, okay? So the leading term when r is large is the monopole, okay, which is just determined by the total charge. The subleading term that goes like 1 over r squared is given by the dipole, and the next, again, is the quadrupole, gives you 1 over cube, and so on and so forth, okay? At the nth multiple order, you the relative importance of the contribution goes roughly like the size of the original system. Okay, these multiples are just sensitive to the size, and they scale like the suitable powers of the size of the object divided by the distance. And now, in this situation, the notion of universality and reductionism are very simply illustrated, okay? So now consider somebody who performs measurements, okay, at some fixed accuracy, okay? I don't know, 1 in a million, okay? And now, if this scientist is at very large distance from the object, r large, in order, with the given finite accuracy, this person can only measure a finite number of multiples, okay? So multiples, let's say that if the precision of the instruments, of their instruments, is 1 in a million, and it's been determined that A over R is about 1 in 10, it's enough to go to the third order, right? If you go to beyond the third order, give you 1 million, so it's 10 to the minus 2 to the 3, 10 to the minus 6. And the larger the distance, the fewer multiples are needed at fixed accuracy, okay? Eventually, if you're very, very far away, you can be happy with just the monopole. And now, and this is not just that you cannot, that you have a limitation, that you cannot, you measure very little and then you don't know much. I mean, you can really make predictions with this measurement. If you are very far away, okay, you do some measurements, let's say in some solid angle around where you are, and perhaps at a distance that is a bit bigger. And from that, you can deduce the first few multiples. And knowing those multiples, you can extrapolate the field at the relevant order where you can measure, also in other region of the solid angle, okay, even at the opposite position, at the antipodes with respect to the object. Okay, you're here, the object is here, you can go, so you're here, the object is here, you can also deduce with the accuracy at which you're working the field on the other side. So you can make predictions, and this type of predictivity is not any different than the one that people use, for instance, just to introduce something that more advanced than electrostatics. People do in quantum field theory, or even, say, for instance, in low energy Lagrangian, you do a few measurements, okay, and from those measurements you predict other experiments. And now, what is universality here? It's just the notion that this object you're looking at, there is a vast set of objects that are different, that are indeed very different, but who share the same few multiples, the monopole and the dipole, and this object will look the same. In other words, there is a large variety of different objects that is described in the same class by the same multiple. So in other words, all the details, most of the details that characterize this system, which are codified by the higher multiples, are on one hand hard to measure because you have a finite precision, and also not needed to make predictions. Okay, so therefore you have what we call universality. You have by all practical means the very details of the short distance physics are not needed for you to do physics successfully, if you want. And this fact, the fact that when you go to long distances, this is what happens, is precisely what allows us to do physics. Okay? In other words, to do atomic physics, you don't need to know the standard model. And in a sense, to do the standard model, modulo perhaps some of the questions or the structural conceptual question, but to do prediction in the standard model, we don't need to know string theory. Okay, that's precisely, it's the same story as we have here. Okay, so universality, or if you want, the fuzziness of long distance physics is what allows us to do physics. But of course, it's a limitation, okay, because it does not allow us to know what really is going on there. And in fact, what's going on there is associated to taking the opposite limit, okay? If you have a fixed accuracy, and now you're going to shorter and shorter distances, in order to be able to predict what goes on the other side, or in fact, now you can measure many more things, the more, in order to match the precision that you have, you need more and more multiple, okay? You need to measure more and more. And then, of course, this indicates that you're learning. It's obvious, right? You're learning more and more about what this system is. Systems that look the same very far away, maybe they had the same total charge, maybe they had the same dipole. Then when you go shorter distances and the quadrupole starts becoming important, you will see they are different. It's the same thing as when you look at two people, you're on the hill, you see two people coming out of two houses. At the first, they look like points. You cannot distinguish them. And then at a certain point, you realize that one is your short friend and the other is your tall friend. And when they get closer and closer, you realize, well, one is in the class of short friends, the other in the class of tall friends. And when they get closer and closer, you will tell which is which, okay? And so that's reductionism is the idea that is intrinsic in the idea that to know more, you have to go to shorter distances. Eventually, when you get at the crucial scale where the distance is of the order of the size of the system, the whole expansion breaks down. It's not useful to describe the system this way. And in fact, it may even happen that when you now study the system and often happens, this for instance what happens in the case of atomic physics, when you go to these shorter distances, you realize that you have a specific model, maybe even simple, maybe the charges of the system are just a few point-like charges, maybe 3 or 4, maybe 6 in the shape of an hexagon, okay? And by doing now careful measurements at these short scales, you can now predict, okay, in terms of very few quantities, all the series of multiples, okay? And then that's, if you want, what you would call a change of paradigm. Now you've got into the next layer in physics. But in order to do physics coherently, you don't need to get down there, okay? Now, the case of electrostatics is emblematic. It's, in fact, if you take it for it is, it's just the template for what we will discuss in a moment about field theory. Maybe it's too simple because it's static and classical is not quantum mechanical. However, the same logic carries over to dynamical situations, namely when there is time dependence, both when there is time dependence and when there is quantum mechanics. Now, time dependence, when there is time dependence, of course, beyond distances, there is also time scales, okay? So very much like this universal description emerges at long distances. When there is time dependence, you expect, we know that the universal description emerge at long time scales. And one obvious and typical example that one uses, that one could use to illustrate the same notion in dynamical situation is given by classical fluids, okay? So we know very well, okay, what is a fluid? It's a system of, you can picture it in terms of a system of hard balls that scatter continuously, okay? They just have continuous collisions, okay? And here there is clearly what before was the length A, the size A of the system. Here we have two scales, time and space. One is the typical length between one collision and the next, how much, the mean free path, and in length, and the other is the mean free time between one collision and the other, okay? L collision and tau collision, okay? So at distances and time shorter than this, the description is nothing but a description in terms of point particles that interact, okay? On the other hand, if you can only resolve time scales that are much longer than length scales that are much longer than the collision length, and time scales that are much longer than the collision time, a detailed description of what happens of these individual particles is not possible. And however, in this situation, there is an alternative description, which is the analog, if you want, of the multiple description I was discussing before. There is a macroscopic description that makes use of other variables, and this is the hydrodynamic description, okay? And in this regime, where of lengths that are much longer than the collision length and time that are much longer than the collision time, you can set up the description of your dynamics in precisely the same way as we organized before the potential in the multiple expansion. You can organize it in terms of an expansion in inverse powers, or in the inverse power of the distance that you're probing, or if you want, in positive powers of the collision time and the collision length, very much like the multiple expansion. So the leading order here, the one that is the analog of the monopole, is nothing but the Euler equation for a perfect fluid, okay? Which is nothing but the Newton equations, okay, that describes the acceleration of an element of fluid, okay? The second derivative with respect to time along the fluid motion is, and the force is simply given by the gradient of the pressure. But this is clearly, it is a description that only works in an extremely long distance and extremely long times. And if you're in a situation where these distances and times are not infinitely large, then you will be sensitive to the higher order, very much like before you were sensitive to dipoles and quadrupoles. And here, the leading correction, the one, if you want, that comes, see, these terms all have one derivative with respect to time and one derivative with respect to space. And the higher orders, they will clearly, understandably, be associated with higher derivatives, because by dimensional analysis, when you correction that go like positive powers of the collision length and collision time will involve higher derivative with respect to time and space. Okay. So the next order, which involves two derivatives with respect to space, is what we call the viscosity. Okay. And this gives the leading short distance corrections. And now you can very much as before argue in a very simple way to yourself, when will this term become important? Okay. So now by applying simple dimensional analysis, okay, so let's work in the regime where we're not, where the fluid is acting as nearly incompressible, so which means that it's moving not too fast. So then you can parameterize the density in terms of the typical density at rest times a function of order 1 that describes the deviation from the original density, the density at rest. And similarly, pressure is related to density, but just by dimensional analysis via a velocity square, because you're familiar from the law of perfect gases as well. So, and in fact, in the description of and what this velocity is, well, this velocity is nothing but the velocity of sound, okay? As you can deduce from the leading equation here by linearizing the fluctuation and studying small fluctuation, you find the sound waves, and you find that the velocity of sound wave is simply given by p over rho, square root of p over rho. So this is just the velocity square. And now you have this other term here, eta, just by dimensional analysis will be related to pressure times an additional power of time. And the only time that can, or if it's even the definition of, so now finally, in other words, when you take into account, as long as we compare pressure and density, we cannot introduce a length scale, a time scale, or a length scale. Okay? We can only introduce a velocity. But as soon as we go to viscosity, then the dimension of viscosity requires introduction of a time length. Okay, and we interpret this time length with the collision time. Indeed, this is also self-consistent if you want, because if you look, for instance, well, what do you expect? Well, you expect that this term here, okay, will become important and comparable to the leading ones, let's say this one, when you're considering motions that happen on a time scale that is of the order of the collision time, unless you're looking at timescales that are much, much longer than collision time. When particles undergo many, many collisions, this macroscopic hydrodynamic description will not work. Okay, so the domain where hydrodynamics works is the domain where this term is bigger than that, and so you can just write this equation. Now, going to Fourier space, okay, in Fourier space, now you have velocity here, drop it, okay, it's the same on both sides, and this dtt will become omega. The gradient square will become k squared, the wave number square, and omega and the wave number are related through the speed of sound. Omega is vs k, if you want. Oh, damn it, I clicked the wrong thing. If you want this relation here, okay, in Fourier space is simply rho omega, much, much bigger than eta k squared, okay? And now, if you take into account the relation between k and omega through the speed of sound, then you get precisely this relation here. Okay? So you get that the domain where you can neglect this first derivative correction, the viscosity term, is the domain where the frequency is much, much less than 1 over the collision time. In other words, where the motion is sufficiently slow that over each period of oscillation, the particles undergo any collision. And that's precisely in the time variable, the analog of what we were doing before in the spatial coordinate for the electrostatic potential. Okay, so that's an example of a dynamical case. You can, but classical, you can similarly do. You can do similar reasoning in the quantum mechanical case. The textbook example of this is the study of molecules in the Born-Oppenheimer approximations. Here, what do we have here? We have two classes, two actors. You have the electrons that are very light and move very fast, and you have the nucleons that are very heavy and move very, very, very slowly. Okay, and so because of this, the motion of the electron and the motion of the nucleons have a hierarchy of timescale, of typical timescales. The frequency, namely the frequency of the electrons, is much, much bigger than the frequency of the motion of the nucleons. Okay, so in this situation, you could do something similar to what we did before for the fluid. In other words, if we want to consider, if we are considering motions, if we are considering movement that happened on a very long time scale, what we can do, we can average over the motion of the electrons and focus on the slow motion of the nucleons. Okay, so in other words, what we can do here is solve the Schrödinger equation in 2 steps. Okay, so in other words, first you find the electron spectrum and you treat the coordinates of the nucleons as parameters, okay? And in the second stage, you solve the motion of the nucleons by considering an effective Hamiltonian for the motion of the nucleons in the effective potential that has been generated by solving the Schrödinger equation for the electrons, okay? So in other words, in this situation, you have, again, the notion of universality. No matter what the original configuration of the electron was, in the end, what matters for the slow motions of the nucleons is its effective potential. In other words, it is imaginable to have molecules that have a different electronic structure, but they have the same number of nucleons organized in the same way, okay, perhaps on a, say, a biatomic molecules. And in the end, the description will be qualitatively similar, okay? And in fact, you may even imagine a situation where actually the frequencies of oscillation of these nucleons, even though they have different masses, they're made of different electrons, they are the same, okay, in principle. In other words, you have an emergence of a universal behavior in the motion of the molecule, even though the microphysics can be very different. Of course, to understand the origin of this effective description, you need to probe the system at shorter times and see the motion of the electrons. And very much like in the case of the electrostatic potential or electrodynamics, you can refine systematically this description, okay, in terms of the analog of a multiple expansion or expansion derivative in the case of fluids. In this case, will be an expansion in powers, okay, of the frequency of nucleon over frequency of the electron, which in the end is going to be an expansion in the ratio of mass of the electron over mass of the nucleon. Okay. Now, the moving in a more formal direction, okay, and this procedure done here, illustrated here for the Born-Oppenheimer approximation, can be formalized in the path integral approach to quantum mechanics. As you know, quantum mechanics can be described in the Schrödinger approach, but can also be described, which is the quantum mechanical version of the Hamiltonian approach, and they can also be described with the path integral approach, which is the quantum mechanical version of the Lagrangian approach in mechanics. Now, the path integral approach is quite illustrative, or quite, if you want, it illustrates, it allows you to formalize in a very simple way, simple conceptually, even though technically it can be complicated, what it means to derive an effective description, okay? Because after all, the path integral, to describe physics, what you have to do an integral, okay? So, and the integration variables are just the dynamical variables. And now, deriving effective description, if you want trivially, although it seems trivially, but it's not so when you do it in practice, if you want conceptually, perhaps, well, okay, you have to do an integral, okay? And you can do an integral the way you please. You're familiar with when you do exercise in analysis, you can slice your integral as you wish, okay? At the end, if you've done things correctly, you will get the same result as your colleague who has sliced in a different way. So now, deriving effective description amounts to doing the following. You take your integration variables, okay, and you divide them, like in the case of the molecule, into two classes: the fast moving, which could be the coordinates of the electrons, and the slow moving, which are the coordinates of the nuclei. And then what you do, you perform your path integral by integrating first on the fast moving ones, okay? The fast moving ones are such, by definition of fast moving, are such that when you integrate them out, okay, and you're only considering correlators for the slow moving ones, integrating them out gives you an effective Lagrangian, okay? In other words, this integral can be written as, of course, I can write everything in this form, okay? An integral can be written in this form, but when these guys are fast moving and these are slow moving, this effective action that you derive has properties of localities like any action we are familiar with, okay? So, and this is what we would call the effective description, okay? And now we can use the effective description that all we use in physics are all based on this. Integrate on the fast moving modes and derive the effective description for that. In fact, all of natural science amount to do that, right? I mean, chemistry, you integrate out even the inner atomic motions, the ones that go faster, and you only leave out the external ones, okay? You just, and then of course, you keep only the variables that are relevant at the scale where you are studying. So in order to close this first introductory part, effective long-distance descriptions are ubiquitous, okay? They are the essence of physics. They are the reason why we do physics. In fact, their universality is the very reason we can do physics. The very fact that when you consider descriptions that are sufficiently long range and in time and space, we've seen it, for instance, in the case of the multiples, the vast majority, the infinite amount of parameters that you would have in principle describing your system, decouple, and you can describe at any finite precision your system with a finite number of parameters. That's why we can do physics, okay? Otherwise, for solving any problem, we would need to go to string theory, and that probably would also not be enough, okay? So in view of this, in other words, this makes us also understand, in a sense, why we can do physics, okay? We can do physics because at sufficiently long distance, time and space, sufficient long time to be long distances, we can use effective descriptions, and in this effective description, only a few parameters matter, and therefore we are within that regime predictive. In view of this perspective, or about what we have seen so far, I think it's natural to expect that all theories of nature, sooner or later, will just be effective ones, okay? Maybe, who knows, one day we'll even have the final theory. I'm not sure we will get there. But for the moment, I think it would be quite presumptuous to think that we are right at a stage where we can really think of a final theory, and it's fair assumption to assume that we are just in the middle of the job, and then we're just trying to explore the next layer. Very much like the guy that is going from long distance to inside the charge distribution. Notice that this should be this point of view on physics, in particular on particle physics, is relatively modern, okay? Relatively, okay? A few decades, okay? Because until a few decades ago, it was understood, at least certainly in the 60s, that a quantum field theory, in order to make sense, had to be very special. In particular, that the quantum field theory was not truly effective. The quantum field theory had to be fundamental. And the so-called renormalizable theories were the template for fundamental theories. And also they had such simplicity, and they all spoke for that. When I started doing physics, this, at least in Europe, this was still widely perceived, and even, yeah, it was still widely perceived. But actually, already in the late 60s and early 70s, Wilson dismantled this perspective, okay, and they showed with many examples that, and in fact, he basically re-understood the meaning of renormalization. And from the perspective that emerged from the Wilsonian work, the work of Wilson, quantum field theory came to be viewed as effective like everybody else, like everything else, not everybody else. And now this is widely accepted, and but it's funny that even when I gave these lectures less than a year ago, there were in the audience some senior guys, but certainly senior than me, that objected to what I just said. They said, no. And then even later on in what I had to say later in my class, that I was not presenting the issue of renormalization in the right way. So still, I will continue saying this way. So perhaps now, I want to go to discuss effective quantum field theory. Perhaps it's a good moment to slow down and take a little break of 2-3 minutes. And since I'm speaking in a vacuum, I don't see your faces. You guys are all masking, you're all masked, okay? I don't see your faces. I don't see whether you say, what the hell is this guy saying? This lecture sucks. No idea, this is very, very bad. So, comments, please. Make me feel alive and try to feel alive yourself.
You can raise your hands, guys, and I can give you, I can allow you to open the microphone.
Where do I see raise hands? Yeah, are you organizing? Are you directing them?
Yes, but you see them in the list of participants. Okay, there's one. So
in the list of participants, there is somebody, Anne-Catherine,
yeah,
who raised her hand.
Please. I thought it was interesting. Yeah, I thought it was interesting in the case of hydrodynamics that you pointed out that at smaller distance scales, you have to go to higher derivatives in time and space. Is that a general statement of theories in which you go to higher energies?
Right, yes. I mean, you're not talking about particles. So hydrodynamics was an example, okay? Now you want to understand about particle physics. So is your question about particle physics?
I guess my question is sort of just more of a general question, like as we go to higher energies in multiple different subfields, is it normal to expect that we would have to go to higher derivatives?
Yes. Now the question is that our experimental precision may not be good enough to see this higher derivative or higher order terms. When you go to quantum field theory, there is both the derivative expansion and the field expansion. Okay, but anyway, but conceptually, we can put them together. Yes, in principle, when you go to higher energy, you can become sensitive to higher derivative, or if you want, you become more sensitive, of course, to what lies at shorter distances, which is at higher energies. So yes, yes, indeed. But it doesn't mean that you will see it, because very much like the guy who is very, very far away, let's say a guy who is very far away from the charge distribution, and let's say it's in certain units is 1 billion away. And its precision, the precision of this guy is, the relative precision on what is measuring is 10 to the minus 3, for this person, it will be very hard to see the dipole, even if it moves slightly closer to the distribution of charge. I mean, this person will have to get much closer to see something new. And very much in like high energy physics, are we guaranteed to see something if we increase the energy by a factor of 10? No, not with the precision we have. So we could even see something without increasing the energy, but increasing the precision, right?
Mm-hmm. And is that the same thing as increasing the luminosity in terms of high energy experiment?
Well, increasing the luminosity is like
I guess that's just more
increasing the
statistics.
precision, if you want. Of course, at a certain point you may saturate, because increasing luminosity, you increase the statistical precision. But of course, there's also the issue of data taking, and you may or may not. At the end, there is a limit. Yeah, but increasing luminosity is in the same ballpark as in increasing the precision.
Sure, got it. Okay, thank you.
Daniele with a very cold name.
Yeah, I thank you for your starting talk. It was very interesting. I have a question about this last slide. If you are not doing it later in these lectures, can you just spend a few words more about this old view and new view about renormalization?
Hopefully it will become more evident in the next subject I will discuss. Now we will really discuss, I will essentially discuss this.
Okay.
In a very simplified and, if you want, childish way. But again, the goal of these lectures is to give you the picture, the perspective. It's a lot less about the technique.
Okay.
No. I think I hope I will answer your question in the next half hour.
Okay. Thank you. Thank you very much.
Noam.
Hi. So sort of piggybacking on the same question, but maybe from a different point of view, just asking, okay, let's say that QFT, as in combining special relativity with quantum mechanics, is not a fundamental theory and is just a set of effective theories.
Well, it's more fundamental than atomic physics and chemistry, right?
Yeah.
In this respect, when you meet a chemist or an atomic physicist, you can say that what you're doing is more fundamental.
Sure, but what I mean is
not more important, of course. Be careful.
No. But what I was trying to point towards was, so would you say that string theory is a fundamental theory, or would you try to say that?
Well, string theory. Okay, go ahead.
My point was more towards, in the end, are you looking towards emergent theories, or are you thinking that there is a theory that is a fundamental theory?
Well, maybe somebody will figure out a fundamental theory with no parameters at all from which everything follows. String theory is already not like that, at least the way we know it, okay? I'm not a string theorist, by the way, I should say, first of all, so I'm certainly not the most qualified person to answer this question with the gravitas of somebody who has thought deeply about it. I have my own perspective that I made by talking to people and by studying whatever I can study. The very fact that you have to do working perturbation theory and you have this coupling, which is controlled by the dilaton, you can take different values. There's something missing in our description of string theory. And it's understood by the people who have thought more deeply about it that perhaps string theory is just itself the iceberg, the iceberg bit of a much bigger or of a different description, and only in certain limit it behaves like string theory. Will this be the fundamental description of nature? Maybe. Certainly will be, very much like you see in the example of electrostatics. Let's say that the guy is far away, sees all these monopole, dipole, quadrupoles. Oh my goodness, is this? Blah, blah, blah. Then the person will get very close, and the person will find that this consists of 3 protons on a triangle, some mysterious thing. And this person will have understood the relative relation between all those multiples, but certainly this person will not have understood the value of the charge of the proton and why they were different, right? So at each stage, there's always something unresolved so far. You see, the very fact, if you want, let me say it this way, the very fact that in string theory, there is an ultimate length scale, which is the string length, is what suggests that this reductionistic race towards the smaller and smaller will end there, and there we may have a fundamental theory. Because strictly speaking, in string theory, you cannot probe distances shorter than the string length effectively.
That's what I was trying to point towards, something emergent in the sense that
oh yes, in that sense.
That's
yes.
what I was going.
In that sense, yes, it's a good question. Yes,
okay.
But
thank you.
Can I? So
Yes.
I consider myself free to continue.
Yes.
Okay. So effective quantum field theory. So let me try to illustrate in as simple as possible a way this notion of effective field theory. Okay, and why, and even the relation between effective field theory and renormalizable theories. Okay. So let me start with the ideology, if you want, the Wilsonian ideology, which is an ideology based on the examples I've shown to you. Okay, there's a guy looking at a distribution of electrostatic potential far away, sees monopole, dipole. There's no reason to think there's just monopole and dipole. There will be all the higher multiples. So there's going to be all possible effects are there, only that at the level of my precision, I can only see the first few multiples. Person doing hydrodynamics, okay, we'll see perhaps viscosity. In fact, I'm not aware if there are people going beyond viscosity. In fact, probably in some domains there exist. I don't know whether somebody went to 3rd or 4th order hydrodynamics. Maybe I should know, but it just comes to mind at this moment. Similarly, in the motion of molecules. So the modern perspective of quantum field theory is that quantum field theory is like all these systems. Okay, all the effects are there. Okay, like in the multiple expansion of the field. Okay, and very much like these systems I described, any quantum field theory, as we see it, as we measure it in some experiment, itself, it's like any product we buy at the supermarket. It has a date of expiry. Okay, any QFT has its own energy scale of expiry or length scale of expiry, below which this QFT that we write as an expansion in inverse powers of the scale, or in inverse powers of the scale, or in positive powers of length. Remember, in all the expansions we had, for instance, the electrostatics and hydrodynamics, the higher order terms were always coming with more powers of the fundamental time or length scale. Okay, so doing expansion in these positive powers of length and time scales, given the length and time are the same thing, in the natural units is the same as doing inverse expansion in inverse powers of an energy. Remember, according to quantum mechanics and relativity, energy is inverse of time and energy is inverse of length. So an expansion in positive powers of the fundamental length, okay, is like an expansion inverse powers of energy. So very much like in these other cases, okay, we expect that the short distance effects are controlled by an infinite but systematic expansion in powers of n, which is to say 1 over lambda. Okay, so that's the modern perspective of quantum field theory. So quantum field theory consists of a set of fields. Okay, there will be some rules, maybe there is some symmetries, but let's say we'll discuss symmetries later on. There's a set of fields, and we don't know it, but the theory knows it. There is a fundamental scale, which we can call lambda, where this effective description breaks down, very much like all the other descriptions we have seen so far. And our dynamics, in this case the Lagrangian, will be written very much like all the things you have seen so far as an expansion in positive powers of the fundamental length. It's clear that when the fundamental length is very, very small, which is to say small compared to the length we're looking at, all these higher order effects will be unimportant. Okay? And the expansion in positive powers of length is equivalent to the expansion in inverse powers of lambda. And now we know how things work, right? The simplest example that I can illustrate is the theory of just a single scalar. Okay, so with this idea, we take a theory of a single scalar. Let's assume there is the symmetry phi goes to minus phi, so that we only have even powers of phi in our action. Okay, now what can we say about this Lagrangian? Well, this Lagrangian, we wanted first request is that this Lagrangian, well, we know relativity. Okay, relativity it's a fact of life, so it should be a relativistic invariant. Okay. What else? Well, it should be analytic in phi. Okay, the Lagrangian should behave well when phi goes to 0. Why? Well, because when we do the path integral, we want the vacuum configuration. We want a vacuum to exist, and once that we decide that the vacuum is at a certain point, phi equals 0, the description around that point should be smooth. Okay. So because of this basic request, the Lagrangian will be a generalized infinite polynomial involving expressions of the fields and derivatives. Okay, so start with the leading term, the one we call the kinetic term, the mass term, then there is a quartic interaction. These are the first few things that you can think of. But you can think more. You can think terms with 6 powers of the field, 8 powers and more. You can think of 6 powers of the fields and 2 derivatives. You can think of 4 powers of the fields and 4 derivatives. Now, how do we organize all these terms? We can organize them, noticing that as you're familiar from the basics of quantum field theory, we can just perform basic dimensional analysis. Derivatives have dimension of energy, the field, the action, the Lagrangian has dimension of energy to the 4th. So the field has dimension 1. So this is dimension 4. And so this has dimension, phi square has dimension 2. So this coefficient has dimension squared and mass squared. And in the very same way, okay, we can organize terms that have more derivatives and more powers of the fields. We'll have to have coefficients that involve inverse powers of some energy scale. Okay, and how to interpret this energy scale controlling this expansion? Well, that's precisely like in the case of electrostatics and hydrodynamics. This inverse scale is just the length scale, the fundamental length scale at which our description breaks down. Okay, this 1 over lambda is simply L, and this L is very much like the positive powers. Let me go back, that you could see here. Okay, when you go to the multiple expansion. Okay, remember the multiples by dimensional analysis. The dipole has dimension of length, the quadrupole has dimension of length square, and so on and so forth. And what is the length that enter? Well, the quadruple, all these multiples you obtain by integrating over the region where we have the charge, so they will scale like the size the dipole is A, this is A squared, and so on and so forth. So the situation is exactly the same here. So we're doing an expansion, so the way this happens is exactly the same. So organizing effective theory, the effective field theory you have seen in the lectures of Contino are nothing but the quantum field theory transposition of the multiple expansion. Okay, so they are only richer. In the multiple expansion, you have dipole, quadruple, octuple. It's boring. It's always it's a known set of things. In quantum field theory, you have a much richer set of objects. In fact, the rich set of objects we have has only recently been classified. There have been some recent papers the last 5 years that introduced technology to really classify all the operators. It's the analog of classifying multiples in electrostatics. This is a nice paper, nice mathematical paper by, I'll give you the reference perhaps later on, Henning, Melia, Murayama, and Xu. Okay, so we can organize the Lagrangian as an expansion in inverse power of this fundamental scale that we would call the cutoff scale. And all these other coefficients, okay, the coefficient, of course, there will be the scale, and then there will be some numerical coefficients that are expected to be of order 1, not bigger than order 1. Okay, why? Well, because if they were bigger, okay, if they were much, much bigger than order 1, then the effects of this term would become important and disruptive at energies that are much, much lower than lambda, but lambda is the scale where the description breaks down. So the assumption that lambda is the scale where the description breaks down implies that this coefficient have to be grosso modo less than order unity. They can be small, but they cannot be too large. Okay. On the other hand, it's important that we need something to measure at long distances. Okay, and if this mass here were of the order of lambda, well, there would not be any light long wavelength fields with which to do experiments. So it's necessary that in this whole description, this term here is very, 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 very small compared to lambda. Okay? And we will get to analyzing this situation and the meaning of the situation, what it means later. Okay, but that's a necessary assumption in order to have, if you want, taking m small, it's the same as being allowed to go at large R in the electrostatic case. If you are tied with a chain to the charge distribution, then you cannot go too far. And then you cannot really do this expansion as freely as you want, okay? So it's only if you can travel very far away from this charge distribution that you can really fruitfully do this multiple expansion. And here, the freedom of going to long distances is embodied by the request that this mass should be light. If this mass is not small, then there's no long distance physics. Okay? So now, in this situation, we can now study, okay, very, very naively, working at 3 level, scattering, okay? And what do we learn, okay? Well, scattering, what can we say about scattering amplitude? Well, scattering amplitude up to trivial normalizations, powers of energy, are just dimensionless objects. In particular, the 2-to-2 scattering is truly dimensionless, okay? So therefore, given that the couplings that appear here have suitable inverse mass dimension to match the dimensionality of the corresponding operator, it's just a simple exercise of dimensional analysis to deduce the overall energy dependence of the contribution of each of these terms to the scattering amplitude. In particular, let me consider the 2-to-2 scattering. 2-to-2 scattering is contributed by this term, obviously at 3 level, okay, and by this term, okay. This term contributes to 2-to-2 scattering. This term as well, okay. These ones don't. These ones contribute to 2-to-2 scattering only via loops. But let's analyze things at 3 level. I'll comment on loops in a moment, okay. So working at 3 level, you have this contribution, and that. And now notice that the corresponding coupling have different mass dimensionality up to dimensionless coefficients. Okay, so because of that, the contributions will scale different with the powers of energy. In particular, the contribution of eta 4, okay, will have 2 powers of energy that, if you want, come from when you take Feynman diagrams, converting these derivatives into momenta. Okay, the contribution of this interaction term, just by trivial Feynman rules, to the 2-to-2 scattering amplitude goes like the energy of the process square divided by lambda square. And this actually goes like energy to the 4th over lambda to the 4th. So you have precisely, this is what you have here. Okay? So what can we say here? Well, it's the same as the multiple expansion. When you go to low energy, which is the analog in the multiple case, in the electrostatic case, to go to long distances, you are more and more dominated by a few terms. Okay, remember here there's a whole series, all these infinite series of inverse power of lambda that will come with higher and higher and higher in power of E. Okay, which, remember, E is 1 over distance. Okay, so it's precisely like the multiple. Okay, so but if you go to low energy, which means that you go to long wavelengths, then this term become less and less important. And eventually the only guy that matters is this one. This is the analog of the monopole, if you want, of the spherically symmetric potential, the one that goes like 1/r, is the only term that remains when you go to very, very long distance, at least in this naive three-level analysis. So when E goes to 0, the amplitude is dominated by λ4. But this is not, notice that this is not just the case for the 2 to 2, this is also the case for 2 to 4, okay? Now consider the 2 to 4 amplitude. There are various contributions. There is the, you cannot, λ4 does not contribute because it only has 4 legs. You have to go to the next order in perturbation theory, remaining at 3 level, okay? So you get this diagram here. Well, this diagram has one propagator, and this propagator gives you an inverse power of energy square. Well, that's just the fact that the amplitude 2 to 4 has dimension 1/energy square. But this 1/energy square comes out overall. And again, then you have a dimensionless series, okay? Again, very much as before, the terms that are the contribution of operators of higher dimension, or if you want, operators that come with inverse powers of lambda, will be coming with the suitable powers of energy. And very much as before, when you go to sufficiently low energy, given your precision, then you can neglect all this. And again, you have that your scattering is predicted in terms of just one quantity, which is the same that you could have measured before, okay, in the 2 to 2. So at sufficiently low energy, measuring 2 to 2 is enough to know what happens in 2 to 4. Very much like for electrostatics, you measure in a certain cone, okay, in a certain region of finite region of the angular direction, and you do your measurements, and then you extrapolate at the antipodes. Okay, that's the same thing here. So at low energy, only the lowest dimension couplings matter, and the infinite set of couplings with negative mass dimension is irrelevant. Okay. Conversely, okay, very much like before, if I go to higher and higher energy, or if I increase the precision, then I may become sensitive to these effects. Okay. Eventually, if the energy is so large that is of order lambda, then this description will break down. What will happen? Well, you will discover what is the mysterious physics at the scale lambda, very much like in the case of the electrostatic potential. When you get very close to the distribution, you see inside and you discover what is made of. Okay. For instance, here you can discover that at the scale lambda, you have a new particle with mass lambda, which you integrated out and gave rise to all these interactions. Okay, this is something that could happen. Okay, but something else could happen. The different microphysical description will have different overall Lagrangian. They will have different lambda 6, eta 4, but they may have the same lambda 4. And these different descriptions at sufficiently low energy, they will look the same. In other words, they will belong to the same universality class, the same thing we were saying before. Only to distinguish them, we will need to go to higher energy, to high enough energy. So when the energy, unavoidable, whatever Lagrangian you started with, if you're allowed to go to sufficiently low energy, in other words, if the mass is sufficiently small, that you can go to energies that are very, very, very tiny, you will get to a regime where you can neglect all these higher order terms. Okay, that's very much like electrostatics. And what is left in this regime? Well, the only thing that is left in this regime are the terms in the Lagrangian that do not possess, whose coefficient has positive mass dimension, either 0 or 2. Object with negative mass dimension coefficient will have contributions that are unavoidably suppressed by powers of energy. But how do you call a Lagrangian of this type, truncated this way? Well, this is precisely what we call a renormalizable Lagrangian. A renormalizable Lagrangian consists of a Lagrangian where we have neglected all these terms. So it seems that renormalizability is not a request, but a consequence. It's just an unavoidable consequence of those situations in which I can do physics at energies that are way, way, way smaller than the fundamental scale of the system. Okay, so renormalizability is an emergent property, but it emerges very much like the spherical symmetry of electrostatic potential emerges when you go very far away. If you're very close, it's complicated. But if you go very, very far away, this sphericity of the distribution emerges. But that's an emergent property, okay? It just emerges because at sufficiently long distances, you can neglect all the higher multiples. Here is exactly the same. So it's interesting because, I mean, when I started doing physics 35 years ago, roughly, you could still hear the statement that, well, if the Lagrangian is not renormalizable, then we cannot make predictions. Therefore, it should be renormalizable. Meaning, if it is not renormalizable and we have no perspective on this issue of scale separations, on the fact that we are at low energy, and we put all these coefficients with random values, then yeah, then it seems like we don't know what we are doing, and therefore, but that would just mean that we are in a situation where there's no scale separation. And this could happen, okay? It could have happened that we are in a situation, we could imagine physics where there is no scale separation, where that every new factor of 2, there appear new dynamics, and where things are really tough. But as soon as there is a separation of scales, that here there's a scale lambda, and we can do physics at scales that are much, much lower, then at those lower energy scales, unavoidably our description will be in terms of a normalizable Lagrange.
Riccardo.
Yes.
There was a question in the chat. I don't know if you see it, otherwise I can read it. I think in this context you can.
Okay, I can take another little break.
So can you see it, or should I?
No, I don't.
You have to open the chat. Anyway.
I opened the chat.
But you don't see the question.
I don't see the hand raised.
No, there's not. It's not in the participant.
Ah,
chat.
so in the chat. Sorry.
Yeah, no.
Oh, what an idiot. Sorry, 1 second. Simone Romiti, I have a question. Maybe I missed it. Well, we can go back to that later on, okay? This is a specific question to this system. It may be better to discuss this in the discussion session, but this is simply, look, this is the ratio, I don't know. Simone?
He cannot speak. If he raises his hand, I cannot
speak. So
okay.
The reason why this is the expansion.
Can you hear me? Can you hear me?
Yes, I can hear you.
Yes, this was a question just at the beginning, but if you want, we can discuss it in the.
Well, the reason, so sorry, the expansion is omega is expansion. When you do perturbation theory in quantum mechanics, if you do old-fashioned perturbation theory, you have more and more denominators of E of the, so you say your study some low level, okay? You're gonna have difference of the energy of the high level of the intermediate virtual states minus the energy of your external states, right? Are you familiar with standard perturbation theory in quantum mechanics?
Of course.
And therefore, in that expansion, you have powers of the energy, if you want the frequency associated with the nucleons, you're doing expansion 1 over the energy of the electronic states. Now, how do you relate this ratio? Well, you see, electrons and the nucleons all interact via the same potential, the electrostatic potential. So if you treat them as, they all see the same, essentially, potential. So when you expand around the minimum and you treat this as a harmonic oscillator, the ratio of square frequencies will simply be given by the ratio of masses inverse. That's
okay,
all
it's clear. It's clear. Thank you.
Yeah, this is all I wanted to say. Okay. It turns out that the speed at which I'm talking is about a factor of 2 smaller than the one I was assuming. I have a factor of 2 off, Riccardo.
Where?
In the speed of my lecture delivery.
Factor of 2.
Factor of 2.
Well,
it's just a fact that, and I have a problem, that when I teach online, since I don't see anyone,
you don't see the faces. Yes.
I assume that nobody is understanding and I keep repeating the same thing. That's the problem.
Yeah.
And I would need somebody here, or at least even perhaps a dummy, like a manichino, with the head that does like this. And then I will go much faster.
Okay, but do you
Riccardo,
think...
why don't you do that?
I can look at the...
No. No, okay, look, let me, well, I do what I can.
You can take another 15 minutes, but then at some point we have to break anyway, because then that's Julia's lecture.
Okay, I think another 15 minutes may be difficult, but let me try, okay?
Okay.
So all I said so far was for this theory of scalars, but of course, the same notion applies to theories with gauge bosons and fermions. The overall story is this, okay? You can write the Lagrangian as a series in coefficient and operators, okay? The Lagrangian is dimension 4, and now you can deduce the dimension of the coefficient from this request, okay? So indicating by this the dimension of the operator, the dimension of the coefficient will be given by 4 minus the dimension of the operator. And given the dimension of operators, given these operators are made of positive powers of the fields and derivatives, there are a few operators of low dimension, and there is an infinite tower of operators of arbitrarily high dimension. It's the same thing as the multiples. A few, one monopole, one dipole, and then boom, all the others, okay? Here it is the same, okay? And again, all these infinity, the vast majority of this infinity is effects that become smaller and smaller when you go to low energy, okay? So in a sense, so this dimensional analysis that we just illustrated in the case of the 5 to the 4th, or of the scalar field, applies here as well. The effect of at some energy E, okay, some overall energy E, process that happens with quanta scatter and the quantum energy E, okay, the correction, the contribution to any observable, in particular to the amplitude, the relative importance of each of these terms in the Lagrangian, there are infinitely many of them, will go like, just by simple dimensional analysis, this is dimensionless quantity, will go like G times E to the suitable power of G, right? G has dimensionality and you have to compensate. So, okay, E. And it's clear that all the guys, sorry, this is wrong. This is minus GI. Sorry, guys. How can I correct this? I will correct it. This is there's a minus here in the exponent. Okay. So when the dimension of G becomes negative, the power of energy becomes positive. So okay. So terms with more dimensionality, associated with operators of large dimensionality, are more suppressed at low energy. So for instance, you can even assess the relevance of the mass term. You're familiar that when you work at very high energy, you can treat the mass as a small perturbation, okay? So what is the relative importance of the mass when you compute an amplitude at energy E much bigger than the mass? Well, it will be measured by precisely perturbing your amplitude with 1 power of the mass. Now, in the case of a scalar, the mass enters square, so you perturb your amplitude by m squared, but given the dimension of the perturbation should be the same as the one of the original observable, there will unavoidably be inverse powers of E to compensate. So the relative importance of mass effects at energy E goes like m squared over E. And that means that at very high energy, that's the familiar thing, that at very high energy, you can neglect the mass. But as soon as the energy becomes of the order of the mass, then you cannot, of course, right? At a certain point, the energy cannot even become less than the mass. Okay, so the importance of mass becomes order 1 when the energy is of the order of the mass. In fact, in view of this simple dimensional analysis, we can characterize the couplings in the Lagrangian in 2 broad classes: the renormalizable and the renormalizable, the non-renormalizable. The renormalizable are those that that consist of that correspond to coupling of either positive or 0 dimensions, for which the power here is either 0 or negative. Okay, in other words, these are the terms that affect our physical observables in a way that is either the same at all scales, or it even becomes important at low energy, as it is the case of the mass. These coupling are the one that you normally call renormalizable. And actually, we can even distinguish between 0 dimension and positive dimension. Couplings of positive dimensions, like the mass, are only relevant at small energy, okay? At energies of the order of the mass. While at higher energies, they become less important, irrelevant. While couplings that have 0 dimensionality, then those are equally important at all energy scales. Conversely, then there are the couplings with negative mass dimension, and those become irrelevant when you go at small energy. Okay? Those always affect physical observable with positive power of G. And these are precisely those that we normally call non-renormalizable. There's really this nomenclature that was introduced in the 60s because of complicated technical reasons, maybe complicated, but not as simple as this. They're just distinctions that arise in this simple perspective by dimensional analysis in exactly the same way by which you analyze the system we discussed before, like the electrostatic potential. So these terms are called, they're irrelevant at small energy. Now, there is a language, in the language of statistical mechanics in the renormalization group, these couplings are called irrelevant. These couplings are called marginal because they are neither important in the UV nor in the IR. They're always important. They're marginal. They are always there. And these ones are called relevant. They are relevant at small energy. Okay. Now, this is the analysis at the 3 level. But actually, if you perform the analysis including loops, it just doesn't change quantitatively in any dramatic way. What happens is when you consider loops, okay, and for instance, you can simply consider these papers. For instance, there's a nice paper by Weinberg on effective gauge theories in 1980. The same conclusion holds true when you consider also loop diagrams, but the proof is more technical if you want, but the proof is carried out most easily, for instance, by using dimensional regularization. And all the changes in this simple dimensional analysis they just performed is that when you add loops, you will not just get you will not just get these powers of energy, but you will also get logarithms. Okay, you will get logarithmic corrections. Okay, but as you see, our distinction here was truly genuinely based whether the energy is positive or negative. So something that has some E square adding logs of E will not change. Instead, the terms that are marginal, that were constant, okay, they had a constant effect at 3 level. Here, the logarithm can make a difference, right? Before they were equally important. Now the log can unbalance, can make them more important in the UV or in the IR. Okay, so this can make a difference in this particular case. But again, it's a slow dependence. So in conclusion, what we just said applies. Okay, in any quantum field theory at sufficiently low energy, any quantum field theory at sufficiently low energy is well described by a renormalizable Lagrangian. That's just the result of simple dimensional analysis. And the effects from all the other infinitely many couplings are suppressed by powers of E over lambda. Okay, that's just what it is. And in this perspective, if we have to tell a story, if you have to explain this to a child, okay, there are normalizable terms, okay, the terms that survive when you take very, very low energy limit, you can view them as describing the point-like limit of our particles. Very much like the monopole limit of the electrostatic potential is the one where you treat all this distribution as all the charge in a point. Okay, so these renormalizable terms, they are they are in relation to our electrostatic analogy precisely as the monopole. While the non-normalizable terms, dimension 5 and higher, they describe the inner structure. They start saying, well, this point is not actually a point. It has an extension in one direction. It has some things, okay? It's very nice, like when you do, another example is celestial mechanics, okay? In the very long distance limit, given that planets are all very far separated, you can treat them as points. But if you want to improve the precision of your orbits, you start adding effects, the finite size of the planets, the fact that they rotate, other things, satellites. Okay, these are all additional details that have to do with this inner structure. And here you can beautifully really take this limit if you want. The limit when energy goes to zero is precisely the limit where you become blind to hold the inner structure of this particle. In order to probe this structure, you either need to have a very, very, very high precision, okay, in which you can see this E over lambda, or go directly to high energy. And high precision and high energy are precisely the two themes of particle physics experiments, okay? High energy are experiments like the LHC or the future FCC on HOPES or the Muon Collider, where you push the energy without increasing the precision, okay? And then there are experiments like BEL, which studies B physics, or LHCb, which, never mind, it is at LHC, but these are all experiments that rely on huge statistics, and they relied on these huge statistics in order to have a very, very high precision, okay? But they are probing, the goal is exactly the same, okay? Only achieved in different ways. I think I can stop here. I had a slight extension on this because so far my discussion was more about weakly coupled theory, and all this picture about scale separations and renormalizability and all that. Well, okay, there's a whole other cut to this, which I will discuss tomorrow. Okay, and I think I can stop here.
Okay, let's see if there are other questions. Yes, Francesca.
Yes, thank you. So I did not understand so much the fact that you stressed that only lately we found a way for organizing the different EFT operators, because I just thought that the only criteria for organizing them was the powers of this big lambda.
No, you're right, Francesca. No, what I'm saying is really counting them. Really, you see, many. So first of all, there are, if you then, okay, let's get a bit more technical, okay? So first of all, when you write an operator in the Lagrange, so different operators or seemingly different operators might actually be equivalent by integration by parts.
Yes.
And when you start having objects with many, many derivatives and many, many fields, how do you go systematically in implementing this redundancy? That's not totally trivial.
That's much work.
And the other is that the field variables are, after all, integration variables. And granting the fact that you want your Lagrangian to be analytic at phi equals 0, you can certainly perform a change of integration variables. Let's say send, for instance, phi into phi plus phi squared, which is an equally good variable. Yeah. When you rewrite your Lagrangian in these slightly different variables, you will have a rearrangement of all your operators, right? Because remember, we talk about the Lagrangian as if it was a completely physical thing, but the Lagrangian is only physical up to filter definitions.
Yeah, sure.
So you also have to quotient out of this freedom, and that's also making it non-trivial. Plus, you would like to have a systematic way to do this at any arbitrary order in lambda. So a million fields. So you see, for multiples, we can characterize them for arbitrary high multiple. It's solved, okay? We have an algorithm to write multiples, right? You take product R1, you take a product of x's and subtract all the traces. That's your multiple, and you know how to construct it. We even know how to write them in another basic. These are the spherical harmonics. Okay? So the analog of constructing spherical harmonics for the operators of a quantum field theory, like the standard model, was only solved, or it was only realized recently that this was a problem that could be solved with the technologies that we mostly already knew.
Nice.
Now, not that this, by the way, this is interesting conceptually, even though in practice, we will never do a multiple expansion to a millionth multiple, right? So yeah, this is conceptual and mathematical. Going to dimension 6 is, in the vast majority of cases, enough. In some cases, you need to go to dimension 8. Beyond dimension 8, I bet you that I'm willing to bet we will never need to go.
Okay, so you were talking about this reference by Murayama.
I think it's Murayama, Melia, and Henning, and then the fourth author is my friend. I call him by name all the time. Is Shao. I will. Sorry, don't embarrass me with names. I will put it on the transparencies later.
Okay, thank you.
I don't like to misspell names. When they misspell mine, I get very disappointed. So I don't want to misspell names.
Cool.
But if you search Murayama and Melia, then you will find everything. Okay, it's enough.
Are there other urgent questions that otherwise we have time tomorrow in the discussion session or anyway in the lecture? And I remind you that on Friday you will have both lectures in the afternoon, so you can actually find a way to have a little more time to catch up with things that you left behind.
Well, don't worry, it will always be the first lecture.
Okay.
No, well, maybe the second.
So if there are no other questions, we thank you for this first lecture, and I have to close this session, and we reconvene with all the students at 3:30 for Giulia's lectures. Thank you.
Thank you for the questions and for the attention, even though I cannot see you.